When you interact with an LLM, the system isn't thinking. It executes an equation to calculate the most probable next word in a mathematical sequence. The first hurdle in teaching computers to read was turning vocabulary into numbers. Yoshua Bengio solved this in 2003 with a model that converted every word into a dense list of values. These are word embeddings. By assigning words specific coordinates on a map, the system can quantify meaning. Words with similar roles, like dog and cat, sit close together, while Tuesday and Monday are nearly identical in the model space. This numerical translation gave AI a way to process definitions, but early models had a fixed window. They could only look at a few words at a time, making it impossible to handle long-form text. In 1990, Jeffrey Ellman introduced recurrent neural networks, which process sentences one word at a time. These systems carried a small memory forward, but as the sentence grew longer, the information from the beginning would fade. The 1997 LSTM architecture improved this by adding a notebook mechanism, controllers that decide which information to save and which to delete. This allowed models to track context across many more words. Despite that progress, both systems were sequential. Word 2 could not begin until word 1 was finished. This single-file requirement meant researchers couldn't utilize the parallel processing power of modern graphics cards. Training on internet-scale datasets was a physical impossibility under this architecture. The industry required a system that could look at an entire dataset at once. The 2017 paper, Attention is All You Need, introduced the transformer, an architecture that looks at every word in a prompt simultaneously. This unlocked the ability to train across thousands of GPUs at once. You open a chat window and type out a specific request. Predict the weather of Toronto today. It looks like a conversation, but the computer doesn't actually see the letters or understand the sentence. To the machine, these English words are invisible. To make sense of your prompt, the AI first breaks the sentence into small, discrete units. Common words might stay whole, while a name like Toronto might be sliced into 2 or 3 distinct segments. These tiny segments are known as tokens. By turning your sentence into these individual units, the AI creates a set of data points it can actually begin to calculate. But even a sliced-up word doesn't have a definition to a calculator. It needs to be translated into pure numbers. The AI handles this by placing every token onto a massive multi-dimensional map. It assigns each one a unique numerical coordinate based on how it relates to every other concept the model has ever seen. This coordinate acts like a GPS address for meaning. Words that share a neighborhood, like Monday and Tuesday, end up with very similar addresses. This photograph of Toronto shows a physical place, but to the AI, it's a specific set of numbers representing city, Canada, and cold. These coordinates give every token a generic dictionary-style definition. However, the AI still doesn't know how these words are working together in your specific sentence. Right now, the AI knows Toronto is a place and weather is a concept, but it doesn't yet see the link between them for this specific afternoon. Imagine all the tokens from your prompt walking into a massive, surreal library. This is where the AI does its heavy lifting, across dozens of layers of internal processing. Unlike a person reading a book from start to finish, every single word in your prompt enters this grand library and begins its work at the exact same time. To understand the whole thought, these words have to mingle. They need to figure out which of their neighbors are actually relevant to their own meaning. Every word in the library creates 3 distinct tools to help it navigate the crowd. First, weather sends a searching radar pulse. Who tells me where and when I am? Simultaneously, other words display ID badges. When the radar hits Toronto, it finds a perfect match for location. Finally, Toronto unlocks, revealing its actual substance. This process of matching questions to ID badges is how the AI calculates exactly how much focus to give every word in the sequence. The search succeeds. The word weather has identified Toronto and today as its most important partners. Now, streams of information flow from Toronto and today directly into the word weather, blending their meanings together. The word weather is no longer a generic concept. It has evolved. It now carries the specific weight and context of your local forecast. This focused mixing is the breakthrough that allows large language models to mimic the way humans grasp the nuances of a conversation. Once the mixing is finished, the AI does something counterintuitive. It discards everything in the sentence except for the very last word, today. It ignores the rest because that final word has already absorbed the context of everything that came before it. It's the summary of the entire prompt. This contextualized word now checks itself against a dictionary of over 100,000 possibilities. It assigns percentage scores to every word, looking for the most likely next step. The AI isn't planning its next sentence, it is performing a weighted dice roll. It picks the next word based entirely on the mathematical probability created by that blended context. The machine makes its choice. The winning word is printed to your screen. This new word is immediately added to the end of your prompt, and the entire library process starts again to find the word after that. To keep things moving, the AI keeps a digital notepad of the work it's already done, so it only has to process the newest addition to the string. This lightning-fast cycle of segmenting text, plotting coordinates, and blending context is what allows a computer to turn a simple request into a coherent, human-like response. 175 billion parameter model requires roughly 350 gigabytes of memory just to store its weights. This exceeds the physical capacity of any single GPU currently in existence. To overcome this, engineers slice the model across multiple GPUs. Techniques like zero and tensor parallelism allow a cluster of cards to work on a single request as if they were one machine. Systems like paged attention further optimize this by treating the model's memory like a computer's virtual operating system, allowing servers to handle several times more requests simultaneously. Efficiency also comes from shrinking the numbers. Quantization tools like AWK compress 16-bit weights down to 4 bits, while meticulously protecting the 1% of outlier data that is critical for accuracy. Without these physical optimizations, large language models would be mathematically sound but impossible to deploy on real hardware. The evolution of AI has been a continuous chain of identifying and removing sequential bottlenecks. The architectural shift of the 2017 transformer provided the abstract mathematical blueprint, while engineering breakthroughs forced that math to run on physical chips. What looks like understanding is the combined result of architectural insight and raw computing power. Future progress depends on engineers finding the next inevitable constraint and designing a way to bypass it. The magic of an LLM is simply basic text prediction, pushed to its logical and physical limit.